There is a secret written in the bones of your ancestors, hidden for ages. Inside a Spanish cave, their remains reveal seasonal damage some researchers compare with animals waking from hibernation. Could early humans survive winter by slowing their bodies for months at a time? To explore that possibility, we must descend beneath Atapuerca in northern Spain. At the bottom of a shaft lies Sima de los Huesos, the pit of bones. There, archaeologists uncovered thousands of fossil fragments from 28 ancient individuals. Remarkably, the bones remembered every winter. The fossils are roughly 430,000 years old, from people related to early Neanderthals. Microscopes and detailed CT scans revealed unusual lesions, interrupted growth, and repeated healing. The pattern appeared almost seasonal, as though each winter had left another signature inside the bones. In 2020, two researchers offered a radical explanation. These hominins may have entered deep seasonal torpor. During brutal winters, their metabolism could have slowed dramatically, like that of hibernating mammals. This would conserve energy when temperatures collapsed, plants vanished, and food became dangerously scarce. But torpor is not ordinary sleep. In hibernating mammals, heart rate, breathing, and body temperature fall while stored fat supplies the little energy still required. If ancient humans experienced something similar, their bodies would have faced enormous physiological stress, possibly leaving clues inside their growing bones. The researchers focused on signs resembling metabolic bone disease, especially among younger individuals. They argued that prolonged inactivity, poor nutrition, and limited sunlight could disrupt normal bone growth. Recovery during warmer months might explain the repeating patterns, but this interpretation remains controversial. Critics note that these bone changes are not unique to hibernation. Disease or malnutrition can create similar signals. Humans also have energy-hungry brains and lack the specialized adaptations of true hibernators. Without direct evidence, the fossils support an intriguing possibility, not a confirmed behavior. Yet hibernation is not completely absent from the primate family tree. Madagascar's dwarf lemurs can remain dormant for months, sharply reducing metabolism when food becomes scarce. Their existence proves that primate biology can support torpor, but it does not prove that ancient humans ever did. Hibernation is not one endless sleep. Many animals periodically rewarm, raising heart rate and metabolism before sinking back into torpor. These brief arousals consume precious energy. If ancient humans used a similar strategy, winter survival may have alternated between deep rest and short awakenings. Before hibernation, many animals build fat reserves while food is plentiful. If ancient hominins entered torpor, autumn may have been a season of intense preparation, gathering calorie-rich foods and choosing protected caves. Shared warmth, hide coverings, and sheltered resting spaces could have reduced energy loss. Months of inactivity normally weaken human muscles, bones, and movement. True hibernators somehow protect these tissues throughout prolonged winter dormancy. Researchers wondered whether missing protection caused recurring damage within fossils. The human brain demands energy even while the body sleeps. Deep torpor would reduce circulation, glucose use, and neural activity. Ancient hominins needed unknown protections to survive that metabolic slowdown. The proposed bone damage appeared strongest among younger growing individuals. Their developing skeletons required more nutrients during harsh winter scarcity. Adults may have carried larger reserves and survived stress better. Winters in Pleistocene Spain could become cold, dry, and unforgiving. Edible plants disappeared while migrating animals became increasingly difficult targets. Every conserved bit of energy could determine survival until spring. However, early humans possessed another powerful winter defense: cooperation itself. Groups shared food, shelter, warmth, tools, and constant vigilance together. Perhaps survival required teamwork rather than months of seasonal torpor. Controlled fire could transform freezing caves into temporary winter shelters. Fire offered warmth, light, protection, and opportunities for cooking food. This technology may have made true human hibernation entirely unnecessary. Fossil bones alone cannot reveal exactly how metabolism once functioned. No preserved tissue confirms seasonal torpor within these ancient bodies. The hypothesis therefore remains fascinating, possible, and deeply unproven today. Future fossils may preserve clearer seasonal growth patterns for comparison. Researchers can compare them against known hibernating mammals more precisely. New evidence might strengthen the idea, or finally reject it. Today, scientists study torpor for medicine and distant spaceflight missions. Related cooling techniques already support selected emergency medical treatments today. Astronauts might conserve supplies while traveling across enormous interplanetary distances. Synthetic human torpor still presents enormous medical and biological challenges. Doctors must protect circulation, muscles, organs, and brain function carefully. Safe awakening remains equally difficult and important for future researchers. Modern torpor research returns us to those mysterious Spanish fossils. Their patterns suggest repeated hardship, healing, and remarkable human resilience. Whether hibernating or remaining active, these people endured brutal winters. Whatever caused them, these bone patterns recorded recurring physiological stress. Healing proves those individuals repeatedly recovered after difficult seasonal episodes. Their bodies adapted, healed, and continued growing through repeated hardship. The pit of bones preserved remains from many ancient individuals. Their shared location gives scientists an unusually rich population sample. Patterns across multiple individuals matter more than isolated abnormalities alone. Yet the collection also carries serious archaeological limitations and uncertainty. Water, sediment, pressure, and time gradually altered many fossil surfaces. Researchers must separate biological patterns from damage occurring after burial. Modern scanners reveal internal structures hidden beneath ordinary fossil surfaces. Microscopes identify whether growth stopped, restarted, or simply fractured later. No single method can prove ancient human hibernation conclusively today. True hibernators display coordinated changes across metabolism, hormones, and tissues. Scientists seek matching combinations, not one suggestive bone abnormality alone. So far, the human fossil evidence remains incomplete and ambiguous. Living hibernators have defenses against clots, muscle loss, and damage. Ancient humans would need comparable protections during months of inactivity. Unfortunately, fossil bones rarely preserve those delicate molecular instructions directly. Ancient DNA might reveal whether hominins carried useful torpor adaptations, yet warm conditions and immense age destroy genetic material quickly. Without matching genetic clues, bones must carry the argument alone. Fire, shelters, stored food, and cooperation also reduced winter danger. These strategies leave archaeological traces that researchers can test directly. Human survival likely depended upon several flexible solutions working together. Perhaps these hominins never entered continuous, bear-like hibernation at all. They might instead have used shorter periods of metabolic slowdown. That possibility fits biology better, but remains difficult to prove. Even unproven, the hypothesis changes how we imagine human survival. Evolution may have tested strategies our species later abandoned completely. Our bodies could retain faint echoes of those ancient experiments. Future discoveries could transform this debate with better preserved remains. Scientists need seasonal patterns repeated across bones, teeth, and individuals. Genetic or chemical clues could finally strengthen the torpor case. The evidence proves repeated stress, recovery, and harsh seasonal conditions. For now, ancient human hibernation remains an intriguing scientific hypothesis. Still, the bones preserve something more certain than hibernation itself. Severe, repeated winters left unmistakable marks upon their ancient bones. Whatever their strategy, they survived conditions we can barely imagine. The secret in those bones is not a final answer. It is evidence of extraordinary survival, preserved beneath Spanish stone. Perhaps our ancestors never slept through winter, but they endured it.